Hi, good evening everyone. So for today, we're going to discuss an introduction to a bipolar junction transistor. So as I've mentioned before, transistors were invented by a group of three men at the Bell Laboratories in 1947. So who are those three men? So they were Bardeen, Brattain, and Shockley. So the discovery of transistor was the beginning of a technological revolution that is still continuing. So they are still trying to improve what these three men developed in 1947. So basically, there are two types of transistors, the BJT and the FET. So BJT stands for Bipolar Junction Transistor, while FET or FET stands for Field Effect Transistor. So for this discussion, we're going to focus on BJT first. So there are typically two practical applications for BJTs. So BJTs are used as linear amplifiers and also electronic switch. So as we will be discussing after this, so there are three regions of interest for BJT. So we have the active region, we have the saturation region, and we have the cutoff region. So when the amplifier is, or when the BJT rather is working as an amplifier, that means it is working at the active region. While when it is operating as an electronic switch, it functions, or it works it shifts between the cutoff and the saturation region. We have the third application for transistor, which is as an impedance matching device. So impedance matching device will be tackled later. So BJT is bipolar junction transistor. It is constructed with three doped semiconductor regions separated by two PN junction. So what is a PN junction? PN junction is a diode. So typically, BJT is just like two diodes that are connected back to back with each other. So this figure here shows the basic epitaxial planar structure. So how are we going to create your BJT? So it will be starting with the substrate, and then we have the first dope region. So the first dope region that we have is the collector, and then we have the base, and then we have the emitter. So as you can see, although the base and rather the emitter and the collector is made up of the same material, their doping differs. So what are those three terminals? So we have the emitter, the base, and the collector. And of course, we have here the metallized contacts, so that if you are going to connect your transistor to your circuit, so you're going to make these three metallized contacts. So you have a contact for the emitter, you have one for the collector, and then we have one for the base. Okay, so the three regions are the base, emitter, and the collector. So as you can see, we have two types of BJT. We have the NPN and we have the PNP. So they are just the same. So the only difference is on how are we going to bias them. Okay, so we have the two PN junction. So what are the two PN junction? We have the base emitter junction and we have the base collector junction. So they are just like two diodes that are connected back to back. So for NPN, it is just like you have a cathode, and then you have an anode. Okay, so this is your first diode, and then you have an anode, and then you have your cathode here. So this is your first diode, and then you have your second diode. So your first terminal is your N-type, which is your cathode, and then you have your P-type here, and then you have your N-type here. So it's just technically two diodes that are connected back to back. The other one is the PNP. So how does your PNP looks like? It's just you have your anode here, and then you have your cathode here. So that is your first PN, or that is your first diode, and then you have another cathode here, and then you have another anode here. So this is your first diode, this is your second diode. So you have your p-type material here, and then you have an n-type material here, and then another p-type material here. So basically they are just two diodes that are connected back to back with each other. Okay, so the two PN junctions is the base emitter junction, and you have the base collector junction. So the base emitter junction, this is the PN junction joining your base region and the emitter region. And then the base collector junction is your PN junction that joins your base region and the collector region. So although as you have seen previously, so the emitter and the collector are made up of the same type of material. So for NPN, they are both N types, and for PNP, they are both P types. But you cannot interchange them. So you might be wondering, since they are made up of the same material, can we use the collector as the emitter and vice versa? Can we use the emitter as the collector? So the answer is no, because even though they are made up of the same material, the doping differs. Okay, so what do we mean by the doping? Doping has something to do with the resistivity of that region. Okay, so doping is inversely proportional to the resistivity. So when you say the emitter region is the most heavily doped, so that means you have placed more dopants. Okay, so you have placed either more pentavalent impurities or trivalent impurities compared with the collector region. Okay, so when we say most heavily doped, that means this region is the least, has the least resistance. Okay, so when you say heavily doped, lesser resistance, and when you say lightly doped, so in the base region is the most lightly doped, and it is very very thin compared with the emitter and the collector region. So when we say lightly doped, among these three regions, base region has the highest resistance. Okay, so the most heavily doped has the least resistance. So this is moderately doped. So this has moderate resistance, and this is lightly doped. That means it has the highest resistance. This will explain later about their current. Okay, about the emitter current, about the base current, and about the collector current. Okay, so we have here the schematic symbol for NPN and PNP. So bipolar refers to the use of both holes and electrons. So we have discussed previously that diodes, they have two carriers. So the two carriers are the holes and the electrons. So for bipolar junction transistor, from the term bipolar, it means two. So that means we're going to use both holes and electrons as the carriers or in the operation of your transistor. Unlike the other one, field effect transistor, so that is a unipolar device. So when you say unipolar device, it's just we're going to make use of the holes or just the electrons. Unlike for bipolar, both holes and electrons are going to function for our transistor to operate. Okay, so the main difference between the two symbol is the arrow. Okay, so wherever the arrow is, that is your emitter. So we have here the NPN and the PNP. So NPN is just like you say, not pointing in, and PNP is pointing in. Okay, so the other one, the opposite terminal is the collector, and then this one is the base. Okay, so these are the symbols for NPN and PNP. Okay, so what is the basic transistor operation? So you are already familiar with the forward bias and the reverse bias. So since this is just a diode that is connected back to back, so the forward and the reverse biasing is just like what happens when we discuss the forward and the reverse bias in the diode. So we have here the the important transistor operation. So the base emitter junction must be forward biased and the base collector junction must be reverse biased. Okay, so what do we mean by forward biased? Again, just as a review. So when we say forward biased, we are going to connect your P-type material to the positive terminal and we're going to connect your N-type material to the negative terminal. So when we say reverse bias, we're just going to reverse your polarity. Okay, so what do we mean by this one? So this is the transistor here is connected in a common emitter manner. So as you can see, the emitter is the one which is grounded. So this is common emitter. Actually, we have three basic configurations. So you have the common emitter, we have the common base, and we have the common collector. So for this explanation, this is for a common emitter configuration. So why common? Because emitter is both seen at the input terminal and at the output terminal. So as you can see, what is the input terminal here? The input terminal here is the base and the emitter, while the output terminal is the collector and the emitter. So for proper transistor operation, so the base emitter junction is forward biased and the base collector junction is reverse biased. So as you can see, this is the base and this is the emitter. So this is what type of transistor is this? This is an NPN because as you can see, the arrow is not pointing in. So the base is P-type. So we are going to connect the positive terminal to the base and then the negative terminal to the emitter. So the base is P-type and the emitter is N-type. While reverse biasing, so we're not going to consider this source here because this source is connecting the collector and the emitter. So what we have here is the base to collector. So the base to collector must be reverse bias. So this is the collector and this is the base. So again, this is N-type and this is P-type. So we have a positive polarity at the collector while we have a negative polarity for the base. So this is just the same with a PNP transistor. So this is the symbol for a PNP transistor. So this is pointing in. Look at the arrow. It is pointing in. So look at observe what we did. So what we did is just we reverse all the polarities, okay? Because technically from NPN we just reversed it to PNP. So the positive terminals here became negative here while the negative terminals here became positive here. At the same time, look at the supply. The positive here, this is positive for NPN while this is negative for PNP. Why? Because our base here is N-type. So can we interchange? Can we, since the collector and the base is just the same, either both P-type or both N-type? So the answer is no. We have to forward bias the base emitter while we have to reverse bias the base collector junction. Actually, we can show this in a common base configuration. So how does a common base configuration looks like? So for common base, if we have here let us say PNP. So if I explain this in PNP, so this is just the same for NPN. All you have to do is to reverse the polarity of your sources, okay? So this is your this is your emitter, this is your base, and this is your collector. So this is the emitter, this is your base, and this is collector. So how are we going to explain this base to emitter and base to collector here? So your P-type here, this is emitter to base, so it should be forward bias. So our source here must be positive and this is negative. So for the N-type, you have your negative terminal here. Okay, while the base to collector junction, they must be reverse bias. So since they are reverse bias, so what do we have here? So we have to place positive here for the N-type and then we have to place the negative here for the P-type. Okay, so we call this your VCC and we call this your VBB. So why do we have here common base? So this is common base because base is common to both inputs and output. So what is your input here? Emitter to base. What is your output here? Base to collector. So we can see that emitter to base must be forward biased while collector to base must be reverse biased. So if your transistor is connected in this manner, as you can see, so what is the symbol for your PNP? So what is the direction for your current? So it is usually from the negative to the positive. So if our current is flowing in this manner, so it's just like that. And this one, it is flowing at this manner. So as you can see, both current flows at the same direction. So that means your transistor is operating at the active region, or your transistor is operating as an amplifier. So this figure here is a common emitter configuration because emitter is common both the input and the output, while this configuration here is common base configuration because the base is common for both input and output. So we have the third one, which is common collector. However, common collectors are not being implemented or being used as a an amplifier or as a switch. Okay, so later on I will be discussing why. For common collector, since collector is common to both side, how are we going to explain common collector? So for example, this is your common collector. Okay, so the input here is at the collector to base. So the input for a common collector is for the base to collector, while since the collector is grounded, okay, and the output is between collector to emitter. As you can see, base to collector is already reverse biased because emitter to base is forward while base to collector is reverse biased. So how can we let your transistor function as an amplifier when the input is already reversed? So what do we mean when the input is reversed? No current can enter your circuit. So therefore, common collector is not being used as an amplifier. Okay, so common collector has other application, and that is for impedance matching. So we're going to discuss impedance matching later. So for transistor amplifier, it is usually between common base and common emitter, although common emitter is much more widely used. So later I will be explaining why. Okay, so why is common emitter more widely used compared to common base? Okay, so we have here the BJT in action. So what happens? What happens when when we connect your emitter to base in a forward bias mode while your collector to base in a reverse bias mode? So as you can see, we have here so this is an NPN. So this is an NPN transistor. That means your emitter has what? They have lots of, what is the majority carriers for N-type? So they have lots of electrons because electrons are the majority carriers, while they have minority carriers in forms of holes. So what are the minority carriers in P-type? So the minority carriers in P-type are the electrons, while the majority carriers are the holes, while the minority carriers are the electrons. At the collector side, since this is already also an N-type, majority carriers are the holes, the electrons rather, and then the minority carriers are the holes. Okay, so our main concern for BJT transistor is for the electrons at the emitter to be collected at the collector terminal. So that means all the electrons at your emitter region must be transferred at the collector region. Okay, so in doing that, they will have to pass through the base. So my analogy here, class, is just like you're passing through a, what do you call this, an overpass. Okay, so if you go up in an overpass, so all you have to do is to go down there. So all of the electrons in the emitter region must go to the collector region upon passing through the base. So how is that going to happen? So the forward bias here at the base emitter region, make sure depletion region here thinner. So what do we mean by making your depletion region thinner? So that means your electrons here, which are the majority carriers, can pass through your base, which are what? Which is a p-type material. So since this is forward bias, look at the depletion region. So the depletion region is thin when you have forward bias configuration. So therefore, all of our electrons here can pass through your base. Okay, now what happens to the base? So in the base region, our majority carriers are the holes. So if we make your base to collector region forward bias, so we are permitting the holes to be transferred at the collector side. However, what is our goal? Our goal is for the electrons from the emitter to be transferred at the collector region. So what are we going to do now is we are going to reverse bias your base. Because upon reverse biasing your base, majority carriers cannot transfer from the base to the collector. Now, what is the majority carrier at the base? So since this is NPN, this is P-type, the majority carriers are the holes. So holes cannot transfer from the base going to the collector. So what will happen during the reverse bias mode? Look at the reverse bias mode. So the depletion region thickens. Okay, so the thickening of the depletion region doesn't permit your majority carriers, which are the holes, to be transferred at the collector side. But during reverse bias region, reverse current may occur. So what do we mean by reverse current, or the reverse the minority carriers? They are the one which can pass through the base going to the collector. Now, the question is, what is the minority carrier at the base? So, since this is p-type, the minority carriers here are the electrons. So, the electrons, being the minority carriers now, can pass through your collector. So, you see, the electrons here passes through your base, and those same electrons, which are the minority carriers in p-type, they are the one which passes through the collector. That's why we reverse bias your base to the collector. So it happens like that. Okay, I'll repeat. Electrons here being majority carriers and being forward biased, they pass through your base, and then these electrons here are the minority carriers, and being reverse biased, minority carriers are the only one which can pass through the base to the collector, which happens to be the electrons. So as you can see, the electrons passes through the emitter going to the collector, passing through your base. So also explaining why it's called bipolar. Why? Because the electrons here mingles with your holes here. So both holes and electrons participated in the action of your transistor. Okay, so that is your BJT action. Okay, now let us go to current. So since there are three regions or three terminals, so we also have three currents. Okay, so the arrow on the emitter of the transistor symbol points in the direction of the conventional current. So the emitter current, this is the highest current among the three. This is the sum of the collector current IC and the base current IB. Okay, so technically, as you can see, look at the arrow. So the arrow symbol from your emitter shows the direction of your three currents. So KCL class, no? So if IE is leaving, so therefore both IC and IB is entering your transistor. While in this one, when your IE is entering your transistor, so both IC and your IB is leaving your transistor. Okay, so IB is very small compared to IE and IC. So the capital letter subscripts indicates DC values. Okay, so later on, we're going to discuss separately the DC and the AC analysis. So we're always using capital letters for DC analysis. This also explains the doping class, no? If you remember from the previous slide, we said that why IB is very, very small, because base is the most lightly doped among the three regions. So since it is the most lightly doped, it has the highest resistance. So that explains why IB is very, very small. And then IE is the most heavily doped. So since it is the most heavily doped, it has the lowest resistance. So that explains why IE has the highest current. Okay, and IE is approximately equal to IC. So that's our goal, right? For the carriers from the emitter to be transmitted or to be collected at the collector terminal, just passing through the base. So that means our current made up of the majority carriers from the emitter must be transferred to the collector. So that's why they must be approximately equal. Okay. So this is your transistor bias circuit. Again, this is for an NPN and for a PNP transistor. So as you can see, following the current direction. So this is your IE, and then you have your IC and you have your IB. So for example, how can you make your IB flow in this direction? So it must be from negative to the positive. So it must be plus, minus, plus, negative. Okay, so for your IC to flow in this manner, so it should be positive here at the collector while negative here at the emitter. So we have here your emitter is grounded. So you can see emitter both at the input side and the output side. All you have to do is to reverse the polarity for PNP transistor. Basically, they are just the same. What differs is the direction of the current, and what goes with the direction of the current, the polarity of your sources. So in our examples, we always use the common emitter configuration because as I said before, common emitter is widely used as an amplifier circuit. Okay, so we have here transistor characteristics and parameters. I'm going to introduce to you some parameters that we're going to make use that is important in our future computations. So we have DC beta. The symbol is this one. So beta, we can see beta in common emitter configuration. Okay, so common emitter configuration, you have beta, you have alpha. So alpha is being used in common base configuration. So with third one, that is your gamma. What is the symbol for gamma? I forgot the symbol for gamma. Like that. Okay, so for gamma, this is for common collector. However, as I've said, common collector is not usually used, so therefore gamma is not often used in the computation. So for beta, common emitter, so this is the ratio of the DC collector current IC to the DC base current. Actually, this is the ratio of the output current to the input current. Okay, so for common base, what is the input for for common emitter? So what is the input for common emitter? So the common emitter is common both the input side, and the emitter is common both the input and the output side. So the input for common emitter is the base, and the output for common emitter is the collector. So therefore, getting the ratio between the output and input current, so beta is equal to your output current, which is your collector current, all over your base current, which is IB. Okay? So this is also called the DC current gain of a transistor. This is a higher value. This one has a higher value. So its typical value ranges from less than 20 to 200 or higher. All you have to remember is when we're talking about beta, it is always greater than 1. Why? Because IB can never be greater than IC, or IB cannot be equal to your IC. So usually IB is very, very small. So therefore, being at the denominator, we will always be getting beta, which is greater than 1. So if you computed beta that is less than 1, so you have to repeat your computation, because definitely there is something wrong. Okay? So the alpha, you can see alpha in common base configuration. So why common base? Because the input for common base is the emitter, and the output for common base is the collector current. So getting the output current, the ratio of the output current to the input current, so the output current is IC and the input current is IE. So that is our alpha. Now, beta only occurs at common emitter, and alpha occurs at common base, because it is only in common emitter that your input is base and your output is the collector, and only in common base that your input is emitter and your output is the collector. So from the ratio, you can see that alpha is typically small. Okay, it is lesser than 1 because IC is always lesser than IE. So IE has the greatest current among them. So typically, alpha ranges from 0.95 to 0.99 or greater, but is always less than 1. Okay, because IC is just approximately equal to IE. It's not equal to IE. Why? Because we always have the base current. Although it is very, very small, it usually range in microampere values, but still IC is not equal to IE. So technically, it is always lesser than 1. Okay? So we have here a very simple example. So this is a very simple example, class. All you have to do is to use your calculator here. So this is just addition, subtraction, and multiplication. So we have here determine the current gain, beta. So why do we refer beta as current gain? Because as you can see, what is your input? Your input is IB, which is typically small, and then your output is IC, which is typically higher. So you have a small input current with a high output current. So there is a gain in your current. So therefore, beta is also called a current gain. Okay? So determine the current gain. I think I have to reverse my paper here. Okay. So you have to determine the current gain beta and the emitter current for a transistor where IB is 50 microampere and IC is equal to 3.65 milliampere. Okay, so I think this is direct substitution. So what is IE? IE is just the sum of your IC plus IB. So just take note of your micro and your milli. Okay, so IC here is 3.65 milliamperes plus you have here 50 microamperes. So take note how small your IB is compared with your IC. Now, I forgot my calculator. So this is my daughter's calculator and I really don't know how to use this. So can you compute that for me? We have here 3.65 exponent like that, negative 3, is that correct, plus 50 exponent negative 6 for micro. Is this correct? The answer is, so this is 3.7 milliamperes. So simple addition, okay? So just bear with me with the calculator because I'm not really familiar with the calculator. So that's it. Just as simple as that. And then we can compute for beta. What is your beta? That is your IC all over your IB. So that is 3.65 milliamperes divided by 50 microamperes. So simple. So we have here 3.65. Can you see this? Exponent minus 3 divided by 50 exponent minus 6. So that will give you 73. So our beta is always greater than 1. Okay, so very simple. Let's have another example here. A certain transistor has a beta of 200. So when the base current is 50 microamperes, we're going to determine the collector current. So in this case, we are given the beta. So beta is, this is 200, which is equal to IC all over base current, which is 50 microamperes. So we wanted to solve for IC. Okay, so IC is equivalent to 200 multiplied by 50 microamperes. So giving us the value of IC, 200 times 50 exponent negative 6. So that is equivalent to 0.01 engineering notation. So that is 10 milliamperes. So IC is equivalent to 10 milliamperes. Okay, that's it. So what if ma'am, what if I am connected in common base and the beta is given, or vice versa? So can we have a relationship for beta and alpha? Because as I've said earlier, alpha is for common base configurations while beta is for common emitter configurations. Usually, beta or HFE is the one which is given in a transistor specification sheets. But what if beta is given and we wanted to connect your transistor in a common base configuration? So what we need is alpha. So do we have a direct relationship between beta and alpha and vice versa? Yes. So for if you are given beta and you wanted to solve for alpha, so from whole number greater than 1, so we wanted it to be a lesser than 1 number. So alpha is given by beta all over beta plus 1. So this value here will always give you a lesser than 1 value. Okay, but if we wanted to solve for beta, okay, and if we wanted to solve for beta and we are given alpha instead, so we need a value that is greater than 1. So this is given by alpha divided by 1 minus alpha. So that this will give you a value that is greater than 1, and that corresponds to your beta. So you have to remember these two relationships because you will be needing this. Okay, so when beta is given and you wanted to connect your transistor in a common base configuration, so you will be needing those relationships. Okay, so the first we will be analyzing your BJT circuit. We will be analyzing your BJT circuit separately. Okay, so you have DC source, you have an AC source. So what do we do when you have two sources? So if you can still remember superposition theorem, we usually analyze them separately. Okay, so we're going to analyze first the DC sources. So we're going to neglect your AC source first, and then eventually we're going to analyze your AC source. Okay, to start with our analysis, we have here the BJT circuit analysis. So what do we usually look for in a BJT circuit analysis? So we usually get the value of these parameters. Okay, so what are those parameters? So we have so if you're going to look at the subscript, all of them are in capital letters. So that means we are analyzing the circuit DC first. Okay, so usually we have to determine the three currents. So what are those three currents? You have the base current, you have the emitter current, and you have the collector current. And then we have to analyze three voltages. So we have the VBE. So what do we mean by VBE? So when you have a subscript like VBE, so the positive terminal, if that is in the laboratory, and you have a voltmeter, so you place the voltmeter at the base, while the positive terminal of the voltmeter at the base, while the negative at the emitter. Okay, so the first letter here signifies the positive polarity, while the second here signifies the negative polarity. So you have the VCB, that is the collector with respect to base, and then you have the VCE, which is the collector with respect to the emitter. You can also encounter voltages, such as you're going to determine VC, you're going to determine VE, and you're going to determine VB. So what do we mean by VC, VE, and VB only? So in these cases, the positive polarity is at the collector, at the emitter, or at the base, and the negative is at the ground. So when you have VC, VE, and VB, this is always with respect to the ground. Okay, so remember that. So we have here the collector characteristic curve. So what do we mean by the collector characteristic curve? So this shows how the collector current IC varies with your VCE for a specified values of your base current. So just like in diode, we have your diode equivalent circuit. You have the diode curve, right? So shows the characteristic of your diode, the diode characteristic curve. We also have a characteristic curve for BJT. Okay, so this shows how IC varies with your VCE. So usually the collector characteristic curve is being shown at the output terminal, because the output terminal is between the collector and the emitter. Okay, so what happens to VCE when IC increases, or what happens to VCE when IC decreases, with a specific value for IB, or base current IB. So VBB is the source at the base. So VBB is set to produce a certain value of IB, and VCC is 0. Okay, so when this is the case, when your VCC is equal to 0, it is said to be in a saturation region. Okay, so as I've mentioned earlier, we have three regions of interest. We have the active. Can you still see my so we have the active region, so we have the saturation region, and we have the cutoff region. So when you are in the active region, your transistor is operating as an amplifier. Okay, so when you are in the saturation region and cutoff region, so we use this both. So your transistor rather is operating as a switch. Okay. So what do we mean by saturation region? Both junctions are forward biased. So when both junctions are forward biased, so both forward current occurs. So this will give you the highest possible value for your collector current. Okay, so when we say saturation, this is a state of a BJT in which the collector current has already reached its maximum and is already independent of the base current. As you can see, collector current is dependent on base current because when you use this formula, we have here IC is equivalent to beta multiplied by your IB. So when your IB increases, that's your IC. But when we reach what we call IC saturation, this is a state for a BJT wherein collector current is already at its maximum. So even though we decrease or increase your beta, IC doesn't follow anymore. So that is IC saturation. So you imagine, class, we have a sponge and that sponge cannot hold any droplets of water anymore. So that means it is already saturated. So that is a state in a transistor. If that is the case, we have here your saturation region when it functions as a switch. So maximum current. So what do we mean by when you have a maximum current? Your circuit is in the on state. Okay, so VCC is 0, but your IC is maximum. So what do we mean by when your IC is maximum? So that means you have a short circuit. So short circuit, then that means your switch is in the on state. Now, so your VCC is increased. As your VCC is increased, your VCE increases as the collector current also increases. So this is the IC versus VCE curve for one value of your IB. Okay, so this is your saturation region, maximum current, and this is your breakdown region. Okay? So your VCE exceeds, as your VCE exceeds 0.7, your base collector junction becomes reverse biased. So when your base collector junction becomes reverse biased, what happens? Your transistor now is operating at the active region. So when your transistor is operating at the active or linear region, that means it is operating as an amplifier. So what do we mean by that? Your IC levels off and remains essentially constant for a given value of IB as VCE continues. As you can see, in our formula for IC is independent of VCE. So even though VCE continues to increase, what happens to your IC? It will not change because IC is only dependent with IB. Okay? So IC increases very slightly as VCE, but IC is what? Increases or decreases with respect to IB. In this case, class, as you can see, transistors or BJTs are also called current controlled devices. So what do we mean by current controlled devices? So VCE is not the one which controls the value of your IC. Even though we increase or decrease your VCE, as long as it already exceeds 0.7 volts, IC is independent of that. So which affects IC then? Only IB. Okay, only IB affects IC. So therefore, what is IB? IB is a current. So therefore, BJTs are current control devices. Why? Because IB controls your IC. Okay, whatever happens to your IB will have an effect on your IC. So that is the active region. Okay, so active region, your amplifier is, your transistor is operating as an amplifier. So as VCE reaches a sufficiently high voltage, reverse biased base collector junction goes into breakdown. So the collector current increases rapidly, so it should never be operated in this breakdown region because if you do that, you can damage your transistor. So this is your IC versus VCE for several values of IB. So this is your IC class and this is your VCE. So as you can see, the value of IC doesn't, sorry, the value of your VCE doesn't affect your IC. So which parameter affects your IC or has an effect on your IC? So it is your IB. So as your IB increases, your IC also increases. Okay? But they are not equal. Why? Because IB is in the microampere range while IC is in the milliampere range. So which explains this relationship? So this explains this relationship. So this is very important in our succeeding discussion. Okay? So what happens when IB is equal to 0? So when your IB is equal to 0, your IC is equal to 0. As simple as that. Okay? That means your transistor is operating at the cutoff region. So what do we mean by cutoff? So at the cutoff region, your switch is now in its off state. Okay, off state, when your current is equal to 0, that means you have an open circuit. And when you have an open circuit, that is equivalent to an off state. Okay, I'm going to bring back the slide. As you can see, when your IB is equal to 0, supposedly we don't have any current. But we have a small current here. We call that your leakage current. Okay, so actually, that is not very ideal because technically speaking, when your IB is equal to 0, your IC must also be equal to 0. But that is not the case. We have a very small leakage current. Okay, so again, when your transistor is operating as a switch, it goes from saturation, the on state, to cutoff and vice versa. So the on and off state. But if it is working as an amplifier, it is working at the active region. Okay? So we have a very small collector current. We call that very small collector current as your leakage current. So at cutoff, your VCC is approximately equal to VCC. That means we don't have any drop at RC. So when you don't have any drop at RC, so your VCC is equal to your VCE. Okay, so actually we have a very small leakage current there, and for common collector configuration, common emitter configuration rather, we call that ICEO. So what does ICEO stands for? It is the collector to emitter. See, this is the collector going to the emitter, the collector to emitter current. What is missing here? Base. When the base is open. So what signifies that the base is open? Your IB is equal to 0. Since the base is open, base current is equal to 0. So what is existing here is your leakage current, which is ICEO. ICEO only happens in common emitter configuration because that is the collector to emitter current when your base is open. So at saturation, what happens to your saturation? This is varying IB, so your base is no longer open, so IB is existing. And then what happens to your IC? IC is maximum. Okay, so when IC is maximum, your drop across ICRC is equal to your VCC. So that means VCC minus ICRC, this is equal to 0. So when your VCE is equal to 0, your IC is maximum. So that means you are in a saturation mode. Okay? So VCE is equal to 0, saturation. VCE is equal to VCC, cutoff. Any value between 0 or VCC, your transistor is operating at the active region. So this is your DC load line. Okay, so on our next video, we will be discussing the DC load line. So the DC load line will be coming from your DC circuit. Okay, so you have here your characteristic curve, and then you're going to draw the DC load line. This will, if you still remember our DC analysis or our load line analysis in our diode discussion, so it's the same. So we will be drawing a straight line. So the straight line will be coming from your circuit. The intersection will be your Q point. Now, if your Q point is slightly near this is the y-axis, or the collector current axis, so that is near your IC sat. So when your Q point or your quiescent point is at this point, so that means you are in the saturation region, while when your Q point here, that means you are in cutoff. So when your transistor is operating as a switch, your Q point is transferring from saturation to cutoff and vice versa. So you're just like turning on and turning off your switch. So that is your load line. Okay. So more about beta. So beta varies with collector current and with temperature. Okay, so usually we can see the value of beta. It is specified in your transistor specification sheets, but it is not usually constant. Okay, so beta can be very dependent on the collector current and at the same time with the temperature. So maximum transistor ratings. So this shows we have here different Q points. So when your quiescent point doesn't lie between the saturation and the active region, so for example, it is in point B or point C, so that means it is in the active region. So anywhere between the saturation and the cutoff region is your active region. Okay, so however, we have maximum transistor ratings, so we have to limit the operations, because if we exceeded these ratings, we might damage your transistor. Okay, so the maximum transistor ratings limitations, it gives limitations on its operation. So usually it has something to do with the collector to base voltage. Excuse me. So it has something to do with the collector to base voltage, the collector to emitter voltage, emitter to base voltage, collector current, and power dissipation. So we have to limit, or we have to make sure that we do not exceed those maximum transistor ratings, so that we will not be damaging your transistor. Okay, so as much as possible, we have to place the operating points somewhere far away from the maximum transistor ratings. So the rating power max, so PD max or power dissipation, is usually specified at 25 degrees Celsius. So usually it changes for about 2 milliwatts per degree Celsius. So whatever that is written in the specification sheets, it might change with an increase in temperature. So whatever written there is always at room temperature. So take note that every time you use your transistor in the circuit, there's a tendency that your circuit will heat up, temperature may rise, so therefore your maximum power dissipation will also increase. So this is how your transistor data sheet looks like. Okay, so you have here the terminals. We have 1, 2, 3. So when you use this in the laboratory, so 1, 2, 3 specifies 1 is the emitter, 2 is the base, and 3 is the collector. But that is not always the case. So you really have to look at the data sheet so that you can determine its terminal. And in the laboratory, you can use your voltometer, your VOM, in determining the terminals of your transistor whenever your transistor datasheet is not available. Okay, so we have here the maximum ratings. Those parameters mentioned earlier. So it is written here. Okay, so you have a minimum and maximum value. So every time you make use of your transistor, you have to look at their transistor datasheet to make sure that you do not exceed their maximum values. So transistor packages and terminal identification. So we have here transistor categories. They are categorized in different three different types. So we have the general purpose or small signal devices. These are low or medium power amplifiers or switching circuits. We usually make use of this type of transistors in the laboratory. So when we're doing experiments in the laboratory, usually those are general purpose or small signal devices transistors. Okay, so power devices, usually they are make use for power amplifiers. They're capable of handling higher powers, higher current, okay, used to handle large amount of current, usually in ampere range. So usually pag general purpose, it is in a milliampere range. So power devices, 1000 milliampere or about 1 ampere. And then RF devices, RF radio frequency devices, they are designed to operate at extremely high frequencies. Okay, so since we are using them as an amplifier, frequency is also a factor. Usually RF devices, they are designed to operate at extremely high frequencies. So these are some figures. These are the usual transistor that we're going to see in the laboratory. We're going to perform experiments using this one. And then we have what we call top hat. And then some transistors already in the form of an integrated circuit. So we have here your flat pack. Okay, transistors. You have dual inline package, and then you have your top hat package, and then you have your general purpose transistors. Okay, so we have your power transistors. As you can see, since they will be handling higher amounts of current, they have a heat sink. Okay, so these are heat sink so that they are capable of higher, dissipating higher amount of power. Okay. And then these are the different types of RF transistor. So still three terminals, the emitter, the base, and the collector. So they just differ in their physical appearances. So of course they are quite bulkier because they are being used at higher frequencies. So troubleshooting, how would you troubleshoot a transistor? So you can encounter this in the laboratory when you have your, or in multi-sim, since we are in community quarantine. So the proper voltages is like this. Okay, so your base to emitter must be around 0.7. So why? So you have, this is forward bias. So this PN junction, so when your PN junction is forward biased, when your diode is forward biased, so what voltage we usually read across the diode? So it's 0.7 for silicon or 0.3 for germanium. So since we are using silicon uh, as our main type of transistor, so that means you might be reading around 0.7 or in the neighborhood of 0.7. The collector to emitter, okay, so the collector to emitter, you will be reading any value between 0 to 9 volts. Okay, why? Because if it is 0, that means you are saturated. If it is 9, sorry, if it is cut off. So therefore, somewhere between 0 and 9. So usually between 25 to 85% of your VCC. So that is the proper voltages that we expect. So typical faults and symptoms, okay? So when you have your open base resistor, so when your um, base resistor is open, so what do we expect? Of course, no current, no base current would be entering here. So since no base current will be entering here, collector current must be equal to 0. So therefore, no drop across your RC. So what do we expect at the VCC? So whatever your at your VCE, so whatever your VCC is, you can read it there. So that means your technically your transistor is operating at the cutoff. Okay? So when your collector is open, so when your collector is open, that means no current is entering here. So although we can read 0.5 and 0.7 here, so this is correct, but since this is microvolts or almost 0, that means your RC is the one which is open. Why? Because we have here a correct reading, so between 0.5 to 0.7. So the symptoms, so open collector resistor, readings from microvolt to a few millivolt, because if you have an IB, supposedly you have an IC, but since you don't have an IC, we read 0 voltage between the collector. Okay, so that means your RC is open. Okay, base internally open. So even though your base resistor is functioning, but there is something wrong with the transistor itself, so the base is internally open, you read 0.3 here, which is wrong. Why? We must only read what? Around 0.5 to 0.7. So if this is the case and your RB is not open, so the defective part here is most probably your base. Okay, so we have here collector internally open. So your RC is functioning, your base is functioning, your RB is functioning. At the same time, you can read 9 volts here. So the problem here is your collector terminal. So the one which is not functioning here is your collector terminal. Okay? So when your RB is functioning, your RC is functioning, and still we cannot read anything, so most probably your emitter is internally open. Okay, so when you read 3 volts here and at the same time you read 9 volts here, so there is no collector current. That means 0 volts at the emitter is normal. Okay, so open ground connection, we can read 2.5 volts here. Okay, so that means we didn't connect properly your emitter here. So the fault here is open ground connections. So you can experience these faults when you are performing this in the laboratory. You can also test your BJT using a digital multimeter. Okay, so both junctions should read around 0.7 plus or minus 0.2 volts when forward biased. So both junctions should ideally read open when reversed biased. So what do we mean by open? So we can read a higher voltage. So usually 3 volts if that is the battery voltage for your digital multimeter. Okay, so test test for properly functioning transistor. So forward bias test for base emitter, you should read 0.7. For reverse bias, so that is around 0.6. Forward bias test for BC junction, so 0.7. Reverse bias for BC junction, so you read 2.6. So usually the 2.6 volts is the battery of your digital multimeter. So test for defective, forward bias, and still you read around 2.6 volts. So that means you have an open, okay, typical. So for an open base to collector junction. So when you are reading 0 volts instead, so that that pertains to a short circuit. So either short circuit or an open circuit. Some laboratories, they have transistor testers. So all you have to do is to place your transistor there, the 3 terminals of your transistor, and then the specifications, the parameters will appear on the screen. However, in our laboratory, we don't have these transistor testers. So leakage measurement, we have two types of leakage current. We have already mentioned the ICEO earlier. So ICEO stands for the the collector to emitter when base is open. So ICEO is the leakage current at in a common emitter configuration. Okay, ICBO, what do you mean by ICBO? That is the collector to base current. What is missing? Emitter. When emitter is open. So this usually happens in common base. So ICBO, coming back here, when we open the emitter to base, so supposedly if you have no emitter current, you have no collector current. But we have here your ICBO. So ICBO is the collector to base current when what is missing? Emitter is open. So usually ICBO happens in common base configuration. Okay, so what is the relationship between the two? ICEO is beta multiplied by ICBO. So usually ICEO is greater than your ICBO. Gain measurements, curve tracer. So this is an oscilloscope. An oscilloscope type of instrument that can display transistor characteristics. Gain measurement, if you place the 3 terminals of your transistor, so you will be reading something either in VOMs or in DMM. So usually that's the value for the beta. So the gain. Okay, beta is also called gain. So that is gain measurement. Curve tracer, another way of testing, is an oscilloscope type of instrument that can display transistor characteristics. Okay, so that is the introduction, okay, to a BJT. So for the next video, we will be discussing the DC analysis for BJT. But before we go to that, I would just like to include where did the transistor name came from. Okay, because when we explained about the diode, okay, so when you explained about the diode, we said that diode came from diode, 2 electrodes. How about transistor? So transistor came from 2 words, transfer and resistor. Okay, transfer and resistor. So until eventually it became transresistance, transresistor, and then it became transistor. So what do we mean by transfer of resistor? Because we were able to transfer your current from a low resistance to a higher resistance end without changing its value. Actually, that invalidates the Ohm's law, because we said in your Ohm's law that when your resistance increases, your current must also decrease. But that is not the case with transistors. So as you can see here, we have here your base. Okay, so this is your emitter, your base, and your collector. The emitter to base is usually forward biased. So when it is forward biased, okay, so we have here, for example, let us place a source here. So for example, you have a source here and a load resistance here. So you have here your IE, you have here your base, and you have here your IC. Okay, so if we have here forward bias, if this is forward bias, that means the resistance for a forward bias is very, very low. So if we are going to compute for your I input here, which is your IE, that is your V in all over your R in. But since during forward bias, your R in is usually low, so we have here an I input which is of a higher value, which is approximately equal to your IE. Now, what happens at the collector to base terminal? So this is reversed bias. So when this is reversed bias, this means that your resistance here or your output resistance here is very, very high or infinite. Okay, so your resistance there is high or infinite. But as you can see, because of the transistor here, we can able to transfer your IC here, which is approximately equal to your IE. So your output current IC here is approximately equal to your IE. Okay, so assuming that your base here is equal to 0, whatever I see here, which is equivalent to your approximately equal to your IC, will determine your output voltage here. Okay, so we were able to transfer the almost same amount of current two different resistances here. So it is obvious here that it is possible to have a higher current. Why? Because your R in here is small. But in this area here, we were able to transfer that same amount of current even though the resistance here became higher. So that only make the only thing that made that possible is the transistor here. Without the transistor here, that can never be possible. So that came from two words, transfer and resistor. We were able to transfer the same amount of current to two areas having different resistances. So same current from low resistance going to the higher resistance. That's why we have transfer resistor. So we have transfer resistor until it became transfer resistance, and then eventually it became transistor. So there is where the term transistor came from. Okay, so that's it for today. Just wait for the next video so that we can start we can discuss about the DC analysis. Okay, have a nice day. Good night.